When I was very, very young, I think I've never said this, what I'm going to say now.
You heard it here first.
Yeah, you heard here. Yeah, exactly.
Welcome back to Mastering Complexity. I'm your host, Owen McCall, joined today by a fantastic guest, Mr. Michael Rassias, mathematician extraordinaire, professor, storyteller, military man. You've done it all. I want to thank you for being here and also thank you for elevating the collective IQ of this room significantly.
Thank you very, very much. It was great being here. Thanks.
Now, before we dive into some of the more technical aspects, and I get to showcase my complete ignorance of many of these topics, could you just tell us a little bit about your origin story? Where did it all begin with mathematics?
Now, my life in mathematics actually started very, very early on. My father is a prominent mathematical analyst. He's well known in mathematical analysis. There are terms in mathematical analysis using his name, like the Highest-Ulam Rassias stability in functional equations. So it's a very famous term. He's a famous analyst. So I'm using analysis, but for other fields. I'm working on number theory. So it's independent, but I use similar techniques as the analyst. And probably that happened because my first degree was in engineering.
Okay.
Not in mathematics. So as an engineer, I think more analytically rather than per se algebraically. Okay. But when I was very, very young, I think I've never said this, what I'm going to say now.
You heard it here first.
Yeah, you heard here. Yeah, exactly. So when I was very young, I was not very well, I was young at high school. I was participating in mathematical Olympiads. That is known.
Right.
But why did I participate? That's unknown. When I was at very early high school, you know, they teach you at school what's a polygon, right? A regular polygon, what's a diagonal of a polygon, all these things that, you know, very, very early high school. And so it was for our homework to, in the process of understanding what's a regular polygon, what's a diagonal, and so on, to calculate how many diagonals there are for, I don't know, polygon with, no.
Right.
I came up with a formula calculating the diagonals for any n-gon. So it's n times n minus 3 over 2. And I was ecstatic because I found a general solution. It was my first, let's say, idea of real mathematics, a general formula to calculate the diagonals of an n-gon. I told my father, he was very happy. He said, oh, there's a chance that he's going to become a mathematician. That would be nice. Because when I was quite young, he didn't want to actually pressure me into learning advanced mathematics because he didn't want me to hate it.
Exactly, right? You should come across it yourself. You find a passion for something rather than...
So he said if he likes it, we might cultivate it. If he likes something else, okay. So he was excited, right? I went next day to school. I mean, I like my school, I like my teacher. I don't want to say anything bad about my school. Everything was perfect. But I said that to the teacher and found a general formula replying to the question. I said, okay, a grown-up told you this. I was like devastated. I mean, no, I came up with it. She said, oh, okay, very well. But she didn't believe it. She knew my father is a well-known mathematician.
Case of the parents doing
yeah, and I was like, okay, this cannot go on. So I got back home and I said to my father, this cannot go on. Whenever I come up with a good idea, I was very young. Whenever I come up with a good idea, the people who tell me that it was, you told me this? What do I have to do? So
change your name.
What do I have to do so that this is not the case? When I say something, not in a cocky manner, but you want to be, you know, if you come up with a nice idea, someone will tell you very well when you're a kid. Exactly. Right. That's when he told me, you know what? There are these competitions, mathematical Olympiads. You could try. So I started competing in mathematical Olympiads. I was part of the national team. I ranked first in Greece for a couple of times. And I won a Balkan Mathematical Olympiad, silver medal in a Balkan Mathematical Olympiad, and a silver medal at the International Mathematical Olympiad. And I was actually 15 point something years old when I won that medal, the silver medal. And the problems, the people competing were 15 to 18 with the same problems. So I think I was among the two youngest up until then, among the two youngest to win a silver medal in the history of Greek participations. And when I did that, and then I stopped. I said, okay, it's enough. And then I started studying more advanced mathematics. I knew that I would become a mathematician. But I was interested also in the interconnections with other fields. Mm-hmm. So I actually entered the School of Electrical Engineering and Computer Science of the National Technical University of Athens. And that's a 5-year program. I graduated this program semester earlier than the 5 years, so in 4.5 years. And my thesis actually was in number theory, and it led to my first book. So my first book by Springer was I published that when I was 23.
Wow.
So that was my first book. And then actually I was interviewed for a PhD here at ETH in Zurich.
Say that again, sir. You were interviewed.
So after that,
yep.
I was interviewed for a PhD position at ETH, mathematics department. Okay, and that's an interesting thing that they did, and I liked. I was also accepted for a master's at Cambridge University. Mm-hmm. There's a very famous program called the Tripos, part 3 of the mathematical Tripos at Cambridge. And even though I could start my PhD right away, I asked them, look, I'm also accepted there. Could I go there for a year? I'll learn more things and come after a year. I said, of course. I mean, your position would be here for you. Mm-hmm. You can go there for a year. And that was important because I was exposed to many more interesting things. And I was there to learn because I had my position for a PhD. And that's why I actually chose subjects that were completely different than what I have ever studied. It was, of course, risky what I did because you want to graduate.
Yeah.
Because I thought that it would be very nice to see and learn interdisciplinary things like quantum information theory. It was completely different than some things that I had studied in the past. And people, my colleagues there, the other students were like, are you sure? I mean, people who were taking this class have already taken another 2 classes.
Right, they've got the prerequisites.
Yes.
You're throwing yourself in the fire. Yeah.
But everything went well. And I learned a lot of things and I enjoyed myself. And then I came here. Actually, I was lucky in many parts of this process because also I like to work independently somehow to delve myself into a new problem and discovering what's going on by myself somehow, not going through the standard process of I'll take this class and then the other class. Mm-hmm. It's not really my style.
You're more of a non-linear learner.
For example, I'm a number theorist, right? Mm-hmm. I've never taken the first class in number theory that I've been in was the one I was teaching. I've never attended a class in number theory in order to learn number theory. I learned myself.
Yeah.
And then I taught, while even a PhD, at the end of my PhD, they offered me a class to, not as an assistant, but to teach the class. And that was the first. And then I started teaching every year number theory.
Wow.
Why do I mention this? Because this style also was good with my PhD advisor. So when I started my PhD, he wrote 2 problems on the blackboard. You solve any of the, okay, these are very difficult. He said, if you do something important relevant to this problem, that's a PhD. So I worked on one of the 2 problems for like 6 months. I published a paper, and then my taste was closer to the other one. And I then worked for a year and a half. A year and a half on the second one, I pretty much solved the problem. And so my PhD was around 2-point-something years, 2.5 years. Mm-hmm. After that, I went for a joint postdoc, basically, between the math department of Princeton University. I had to be based in Princeton, but the funding was coming from ETH. So that's the year I was working number theory, But that's the year I met Nash. So at Princeton, they have something that's very good. They have a common room at the Princeton University, and they have a common room at the Institute for Advanced Study at Princeton. That's the place where Einstein was, Oppenheimer was. If you've seen the movie, The Oppenheimer?
Sure.
Okay. There's a scene where Oppenheimer speaks with Einstein. That's at the Institute for Advanced Study.
Right.
It's a very small place. That lake there is like 100 meters from the buildings. It's a small, cozy, family-like place. So both in the Institute for Advanced Study, also at the math department of the university, after lunchtime, 3:30, they offer every day cookies and coffee and tea. And for example, the common room of the math department of Princeton University, also it's a big room with blackboards and so on. And the reason why they took this is so that scientists, young PhDs, postdocs, world-known professors, they mingle together and they exchange ideas, and collaborations start, or you learn things, or you just enjoy your coffee. Okay?
Yeah, I was going to ask, what kind of cookies are we talking about?
Really tasty ones, really. Chocolate cookies.
Okay.
So you can just go for the cookies. Anyhow, that's actually how I met Nash. It was September of 2014, when towards the end of the coffee tea time, he entered the room because he didn't like large crowds in a sense. And I was like shocked. It was like my childhood hero.
Starstruck.
And
right?
yeah, it was exactly. And I then approached him. Actually, I was writing something on the blackboard at the time. There was a conjecture in prime numbers that I actually formulated when I was like 15. And later on, when I became a professional number theorist, I figured out that was a special case of a much more important hypothesis, hypothesis H of Schinzel. Anyway, but for a little while, I published the conjecture, and some people use my name for that conjecture, but it's a special case of something else. It's actually the statement is very simple. Anyone can understand it.
Let's try.
Yeah,
I'm a good testing ground.
So for any prime number p greater than 2, okay, there's there are two other prime numbers, p1 and p2, with p1 less than p2. Okay, so for each prime p, there are two other primes, p1 and p2, such that the initial prime p is equal to p1 plus p2 plus 1 over p1. That's all. Okay, this is still an open problem.
How old were you? 14, 15?
15.
Okay, I got some catching up to do, but I'm with you.
So, I was challenging another guy at tea time at Princeton, and then Nash came in the room and he sat in those big sofas and he saw this and he was interested. And then I approached him and we discussed initially for this and then for problems in the possible interplay between game theory and number theory. And that's how we actually then started discussing about various things and open problems and Hilbert's problems that slowly led for us to the decision of preparing that book together. This would be probably interested for the audience to hear about those problems.
Absolutely.
Problems with Hilbert. It's not about myself, but it's an interesting story. You'll listen again, the story.
Sure.
Great. So, okay, so mathematicians know, of course, about the list of 23 problems of Hilbert, of David Hilbert, but non-mathematicians most probably don't know, of course. What's this infamous list of open problems? The International Mathematical Union organizes every 4 years the International Congress of Mathematicians.
And this is also the body that issues the Fields Medal.
Exactly.
Okay.
Right. So every 4 years, the ICM takes place, and the ICM, they bestow the Fields Medals. Okay. So it's the biggest event in mathematics by far. Okay. And it happens every 4 years strictly, with some exceptions for world wars, etc. But the very first exception was for the second one. So the first ICM took place in 1897 in Zurich. And as I mentioned, Zurich is the only place that has taken place 3 times.
Okay.
We're proud about that. Where's my old hometown, so I'm proud about Zurich. But the first exception, that it didn't happen every 4 years, it was at the second ICM. Instead of happening at 1901, it happened at the beginning of the century. Exactly for that reason, to be at the beginning of this new century of mathematics and to coincide with the Exposition Universelle that was taking place in Paris at the time, because it was organized to take place in Paris. So the most prominent French mathematician of the time, Henri Poincaré, contacted the most prominent German mathematician of the time, David Hilbert, actually proposing to him the idea of composing a list of open problems that would channel and encourage research towards some directions for the coming century. Okay, and Hilbert actually accepted this challenge and invitation, but also a challenge, and he did so, and he prepared a list of 23 problems that spanned through the entirety of mathematics. And as I mentioned, the reference for this piece of information, because it's really unknown, almost hardly anyone knows this, came from Dirk Struik, the correct pronunciation, Struik. He was a professor at MIT, and later in his life he was interested in the history of mathematics. And my father, when he was in his 40s, let's say, he visited MIT, and he happened to meet Struik. Struik was very old at the time. He died at the age of 106, so 106, so he was already very old, but still active, driving a car and so on. And he told this story, and that with Poincaré and Hilbert, how the 23 problems came about. And he heard this story from Hilbert himself.
Wow.
So, yeah. So Hilbert presented those 23 problems.
Are these the so-called, these are the millennium problems?
Okay. No.
Okay.
So David Hilbert presented these problems at the beginning of the new century, back in 1900. So at 2000, the Millennium Prize problems appeared from the Clay Foundation. So with the new century, the Clay Foundation asked from very prominent mathematicians to choose 7 problems that could channel, let's say, the research for the new century now.
I see.
Riemann's hypothesis is one of them.
Yeah.
The Poincaré conjecture was one of them, and when it was resolved, Grigori Perelman did not accept the prize and so on. So there's a lot of drama there.
Sure.
So why do I mention this with the 23 problems of Hilbert? That Hilbert was probably among the last great mathematicians who were able to survey upon the entirety of mathematics, choosing problems, not just choosing, but also him discussing about those problems and directions and so on, right? Being in the core of each problem. And one can say this not because there will be no other Hilberts, mathematicians of that caliber, there will be, but because during the last 100 years, mathematics has expanded so much to so many subfields that life is probably too short to expose yourself in the realm of modern mathematics.
I see.
So having this discussion also with Nash, and I want to really stress this point, and we stress this point in the preface of the book that we prepared, but I want to stress it a lot. We didn't want, even for someone of the caliber of Nash, let alone me, but we didn't want to compare the list of problems that we composed with that of the great Hilbert. That would be it would be blasphemy, right? We just liked the idea of this nowadays can only be something that can be done collectively, a collective effort. And we chose a series of problems that we enjoyed. Some of them famous, some of them applicable, some intriguing curiosities, or some just because we liked it, or for more personal reasons, right? And the reason was not to actually publish the book. Nash is, he liked to see the book published. He actually wanted to see the book published, and he told me that when we decided to publish this book, I'll tell you what we did, but when we decided to actually go ahead and prepare a book about open problems, we would invite also other people to write and so on. He said, look, let's try to have it finished within this academic year.
Okay.
And I said, okay, but don't worry. I mean, afterwards I go to Zurich, but I can come every now and then. You shouldn't worry about this. He said, look, I'm 86. Okay. If something happens to me, it won't wait for the book. and I want to see it published. And look what happened. And the amazing thing is that right before his trip to Oslo to get the Nobel Prize, and now everybody knows there was an accident on the way back. Right before, he said, let's prepare, the book was practically ready. That was a good thing, but right before he said, let's prepare the preface. And I said, well, okay, we have time afterwards. I mean, no, let's prepare the preface. And we prepared the preface describing all this idea with the Hilbert's problems and so on, not to compare it with them. And it's nice that now this can be done collaboratively and so on. And he liked this vintage style. And this rarely happens. He wanted to have at the end of the preface handwritten signatures. So at the end of the preface, we have handwritten, and I told him, look, this is too much. I mean, we publish too much for me, not for you, but we publish this together, that's already too much. We write the preface together, or sign it together, it's too much. Handwritten signatures, as if like I'm like, who knows who. He said, no, that would be nice, to give a nice vintage touch. And So what we did is discussed about various areas of mathematics, just because we liked the discussion on delving into various problems. Things he knew, of course, very well. Some things that they were new for him as well. So we were learning together, in a sense. And we came up with a very long list of problems that we liked, and then a sub-list and a sub-list of the sub-list, because we had to prepare a book as well. So then we came up with a final list. And we said, okay, let's go into more detail for each problem. Who has worked this, have done very important things there, who writes well also, because we want to attract people to work on it, not to push them away. And then we started communicating with people who were world experts on the corresponding problem to write the corresponding chapter and so on. So after my PhD, I went there. This experience happened. And then I came back to Zurich, and I was here for many years. But I was still, as I mentioned, a visiting researcher at the Institute for Advanced Study, and the University of Zurich was very generous, and they provided me funding to go very regularly. So for some period of time, I was going once a month.
Wow.
Yeah, I once calculated the miles that I spent on a plane going from place to place, and it was sufficient, and I'm not kidding, it was sufficient to go from Earth to the Moon and part of the way back.
Seriously?
Seriously, yeah.
Wow.
Yeah.
Now, was this the era when the Learjet was still available? Was it a little bit faster?
So after all these years going back and forth, the Institute for Advanced Studies is an amazing, a magical place. But this could not go on. I mean, it was extremely tiring. And after all these years, a couple of years ago, I decided for completely personal reasons, let's go back to Greece. And I'm lucky because my work is in pure math. And I just need internet connection and a piece of paper and a pen. And my collaborators are still all around the world, and technology, fortunately, nowadays can make the distances zero. So my research goes as it was going in the past, but I moved back in Greece, and that brings us to today. Yeah, I was invited to give the talk here.
Yeah, exactly. Obviously, the pinnacle of your journey. So,
but I'm always happy to come to Zurich and here at Swiss Quant and meet all these people. Dr. Schumann, who's also very much interested in Riemann's hypothesis, and Ashkan Nikabali of the University of Zurich. I really like being back. And
well, you have an open invitation, of course, and the gap between Greece and Switzerland is a little bit better than Massachusetts.
Exactly.
Now, I'm curious. We talked about your work with Professor Nash, rather, and I'm curious. Of course, he was the subject of this famous film, A Beautiful Mind. And in the film, he was sort of portrayed as someone that was maybe a little bit difficult to work with.
Excellent question. Okay, great. Because I actually have written about this.
Okay.
During that period, he was battling with the demons of schizophrenia. So that was, I didn't meet him at that period of his life, he was like a combative personality in a sense. He couldn't be. I mean, it was shocking how wonderful of a person he was. He was extremely simple. He was the most probably the most famous mathematician in the world.
Right.
Yeah, he was extremely simple. He was really wonderful. I mean, he was not arrogant at all. He was like a truly wonderful human being. And I would say when he was still alive, it should be we should call him beautiful mind and a beautiful person.
Right.
Because he was really, really nice, really nice. Yeah, but then everything ended so tragically. Also with his wife. I mean, his wife. You know, they fought all these the tragedies of his life together. All these things that we see in the movie. Of course, the movie. Okay, there's for a movie they present also some other because his hallucinations were a bit different than what they present in the movie. But okay, you have to present in the movie. He was listening to voices rather than seeing people. But how are we going to do that in the movie? But so Alicia was there for him. She was also extremely wonderful. When she was smiling, her full face was lighting up.
Nice.
So it was very nice. And then they left his life together as well. I mean, because in that tragic accident, they were together.
Right.
Yeah.
Poetic.
Yeah. Really.
I saw an interview you did with the BBC as well on your website.
Yeah.
A short.
Yeah, it was a sad event though.
Yeah.
I mean, John Nash became very well known to the general public through the movie A Beautiful Mind, portraying his life. And he became famous due to his work in game theory that was awarded a Nobel Prize in economics. And also due to the struggles of his life. He struggled with schizophrenia.
Right.
And the extremely impressive thing is that towards the end, not the end of his life, at the last decades of his life, he actually overcame this. And actually, I was very surprised because I got very close to him since we published that book together, but it was not just the publication of the book. For 1 year at Princeton, we were almost daily together discussing for hours and hours about mathematics. So if there was something outside the norm, I would somehow identify it. But there was nothing weird.
In like interpersonal communication.
Yeah, so he was completely fine. I think the only thing that was out of the norm, and I think it was just a fear of his, not an actual problem. He was a bit skeptical, you know, when someone he didn't know said hello. So even though he was extremely simple, right? He was not a diva-like personality. He was very simple. So he would discuss with you and so on. If someone completely random said, Professor Nash, hello, because he was like a so famous figure, he would not reply. And I think he was doing that because he was probably scared. What if I say hello and no one's there? He didn't tell me that's what I got, because that was the only thing that was out of the norm. All the rest, you didn't understand that once upon a time there was a problem there. So,
yeah.
And after he passed away, because I was visiting researcher at the Institute for Advanced Study for many years, like 8 years or so, and at the dinner, there were various scientists, and there was a prominent a psychiatrist, a woman that was sitting next to me, and I actually described this. How is this possible? Someone with schizophrenia, then being completely fine. And actually, she said that for the case of men, because it's this disease, in a sense, has hormonal characteristics. It ages with the body.
Okay.
So it becomes weaker.
Interesting. Almost like an allergy to sea fish or something like that.
Something like that. And also, of course, this is an oversimplification. The case of Nash being like a genius, I don't know, it had also other characteristics. Nobody knows what happened there. But yeah, so since you mentioned BBC interview and so on. So Nash, let's go to the beginning of the parenthesis. He was very famous for his work in game theory. He got a Nobel Prize for that. but he also became famous for the reasons I mentioned. But mathematicians, the pure mathematicians, knew that his work in pure mathematics was not just more important, but orders of magnitude more important. And don't take my word for it. I mean, there's people like Mikhail Gromov, probably the most important geometer alive, the Russian mathematician. He has also a Nobel Prize. I mean, a very, very prominent figure of mathematics who has said that repeatedly and wrote about this. But I'm giving that as an opinion of a very famous mathematician, but was the common opinion that his work in pure mathematics, like algebraic geometry, differential equations, and so on, was orders of magnitude deeper. And he had not gotten an award for that.
Right.
Right. So his work in pure math was orders of magnitude deeper than a work that was worth a Nobel Prize. So you get the picture. So people would think, this is a curiosity. I mean, he didn't win a Fields Medal. Fields Medal has an age limit. And
right.
also he suffered from schizophrenia, 40 years old.
40,
and
right.
he suffered also from schizophrenia. So, all these created problems with the age limit. And that year that we were collaborating, that very year, in this long life of Nash, he was awarded the Nobel Prize. So it was like this moment in his life, he finally got this. Everybody knew, of course, that his work was so important, but this proper recognition.
Yeah. And do you consider yourself the common denominator then? Or
Of course
you're
not.
the catalyst?
No, of course not. I was like nothing. I mean, it was Nash, like this unbelievable genius. I was unbelievably lucky and honored, but also lucky to have the opportunity to meet him. But not just that, for someone like him to invest hours and hours of his time and publish something with me. I was like 27, 28 at the time, and he was like in his late 80s.
Yeah.
So, okay, this was an unreal experience. If I have to describe it somehow, imagine that you were a young musician and you had the opportunity to sit close by to Beethoven and not write the Fifth Symphony, but play on the piano with him every day. What would be that?
Sounds incredible.
It would be incredible. It was exactly like that. So we got very close to each other also on a personal level because there was a chemistry actually. That's why all this happened. When you're someone like Nash, you don't need to do. You do something either because you like it or you don't do it.
Right. There's no pressure.
Yeah. So there was a chemistry there, and I could say that I could call him my friend in a sense. He was decades older than me, but we got very close to each other. So you can imagine how shocked I was. We said goodbye. I'll meet you when I come back from Oslo, and then this happened. It was unreal. I mean, I couldn't believe it. And I asked also the university not to forward anything to me about interviews and so on, because it got known that we were working together, so people would expect it. I said, okay, no, it's very sad. Okay, I'll do anything that the university says it's important, it's worth doing. And that's why they forwarded that one. That was an important interview about him and so on.
Now, learning a little bit more about your life, of course, you had some early influence from your father, but you mentioned it wasn't no pressure to become a mathematician, but of course there was some influence there. And very quickly, in your early 20s, you connected with professors of high esteem. Now, another one is Freeman Dyson.
Yeah.
How does he come into the picture?
All this is fresh to me because many people, I'll tell you, but before replying, many people are interested to these stories. And I recently wrote a book about my association with Nash in various levels, scientific and personal life, and very interesting things that are not known to the general public. And various stories that and parallel stories that come into play. It's initially in Greek, but I think it might be translated. So I mentioned exactly what you asked. The reason we met actually was due to Nash. That was the first meeting. when he died at a funeral, okay, I didn't want to speak to anyone, right? And I was about, after a couple of months, to come back to Zurich. And it was May. So, and I didn't think that I would have to go to a funeral. So I didn't have the appropriate clothing, right? So I asked a couple of friends, Greeks who were also researchers there. And one of them gave me a black pair of pants, and another one a black shirt. And the pants were too large, I had to keep them. Yeah, and so it was an unpleasant part of my life. And Dyson was, the funeral was in a semi-closed circle, not too many people, like family, some colleagues, and Freeman Dyson was there as well. And years went by, and then when I started going back and forth at the Institute for Advanced Study, we met at the coffee tea time at the Institute for
I was back to it. Chocolate cookies.
Chocolate cookies. Rude.
I think that's the title of your next book.
Chocolate cookies. Excellent. And actually, as I said, the Institute for Advanced Study is a small place, so you can mingle with all these people. And even though he was old, he was going every day. He was unstoppable, like an eternal teenager. And completely different personality than that of Nash, but very interesting guy. And we happened to talk about our common friend, and he had noticed that I was there in the funeral and I was not in a perfect shape. And he asked me, "How are you now?" and so on. And he told me actually the following story, that he was friends with Nash early on. He didn't know him as a mathematical genius, but as another father of a kid at the school where his son was going.
Wow.
Right? So he was another father. Of course, he knew that he was a great mathematician, but socially like that. And then schizophrenia came. And Nash became very secluded, and that's why they actually called him, you might have heard, the ghost of Fine Hall. Fine Hall is the building housing the mathematics department at Princeton University. So he would roam around at nights writing weird things on the blackboards and so on. And that's why even today, if you go at Princeton and mention the words ghost of Pine Hall, people know that you're talking about Nash. Anyway, so they stopped talking because he became difficult, secluded. He was different. He was not him. And after many years, they saw each other, I think close to the Institute for Advanced Study. And Dyson was not going to say hello because years and years went by and they were not talking for the reasons I mentioned. And then Nash approached him and said, "Hi, Freeman, I saw your daughter on TV. She was great." And then Dyson knew that miraculously Nash was back to the real world because he was watching TV. He knew that person there is the daughter of my good friend Freeman Dyson, and he followed the program and so on. And said, "Oh yeah." And it was really the time that he had actually slowly been resurrected. And he told me this story, and then the discussions. Then we got to know each other with Freeman Dyson, and you know how this is. What are you working on, and so on. And then we discussed about various things. Of course, I wanted to absorb from his wisdom, and every now and then when I was visiting the Institute for Advanced Study, I would drop him an email or call him, whether and we were meeting at his office, and that actually led to him also writing the preface of a book, The Revered with Ashkan Nikebali and Hugh Montgomery, and I had the sad also obligation to write his obituary for the London Mathematical Society. I was invited to do that when he passed away at the age of 96, if I'm not mistaken. That's why I said he was unstoppable. When he was like at 90, he wrote his last book at the age of 94 or something.
Wow. But both these giants kept, it was lifelong learning for these guys.
Exactly, yeah.
Okay. And I'm curious, you got the chance to collaborate with both of these guys.
I collaborate with Dyson. We met each other and we discussed about science, and he also wrote the preface of a book, and so we got to know each other well, but we didn't publish anything together. Yeah. Sorry for interrupting.
No problem. No, we keep it flowing. Absolutely. Now, I'd love to talk a little bit about, and you presented this earlier, a little bit about the story with the NSA and this connection here. So maybe you could tell us a little bit about,
Yeah, sure, of course,
about how this all went down.
Yeah. So, in 2012, a series of letters that John Nash had sent to the NSA in around 1954, 1955, so almost 60 years earlier, right, were declassified. And when these letters were declassified, we had to actually change some parts of history of computer science and cryptography. Because in these letters, so as I mentioned earlier, to recap, he got the Nobel Prize for game theory. His work in pure math was orders of magnitude more important. He got a Nobel Prize for that. Order of magnitude more important, something that was worth the Nobel Prize. But also in secret, he revolutionized modern cryptography. We do not know if these ideas were actually applied, whether they understood, and so on. But who knows? So what's the story? In 1954 and 1955, he exchanged some letters with the National Security Agency of the US. And in these letters, he proposed the architecture for the creation of a parallel processing machine before any such a machine existed. B, he proposed and described the concept of computational complexity before the notion was ever studied 10 years earlier, and then applied this concept in order to create a crypto system. So nowadays, any freshman in computer science or math department knows, of course, computational complexity, and we use it. A bit later on, they will learn about the applications to cryptography, but the concept of computational complexity is commonplace. But back then, they didn't even they had not studied the concept, that was not there. So he came up with the concept and thought that we should apply it to cryptography. So he foresaw computational complexity 10 years ahead and modern cryptography 20 years.
Wow.
And also, he all but formulated the most important open problem in computer science, the P versus NP. Even earlier than the discussion between Gödel and von Neumann, there was a letter that Gödel sent to von Neumann when von Neumann was very sick with cancer, and he said that he sent that to discuss, to make von Neumann start thinking mathematics rather than the fact that his illness, and he passed away a little bit after that. But so these letters, all but stating P versus NP, were even earlier than that. And this was in the dark, this 2012. And Nash never spoke. And I met Nash at the academic year 2014-2015. He never said anything. And of course, even though he could. But you know what my take on this is? The only way to somehow keep a secret of that nature indefinitely, like for decades, and you don't know for how many decades, is to forget it exists as piece of information. It's not there. Because if it is there, and you're waiting, when I'm gonna be able to say, then this game is not for you. You're gonna actually reveal it.
Right.
So it was also in my discussion with him as if this information was not there. And we included the problem in cryptography in the book. So we discussed about problems in cryptography. He never mentioned a thing. We just had those conversations outside, by the way. So, because who knows? Actually, he wanted to have these discussions while walking. So this, so this is a very interesting story. And who knows, probably they used it and they are decades ahead of everyone else. Or they didn't understand the value of it. I don't know.
But you mentioned Freeman Dyson maybe had a take
exactly,
on
yes.
Too, right? Yeah.
See, because Freeman Dyson was part of the Jason team. So it's a team of scientists that advises governments on strategic defense issues. And I asked him about his opinion, and he said that he thinks that probably he didn't reveal anything, of course. I mean, I don't know if he knew something to reveal, but and I wouldn't go there. But he just said that the level of understanding back then in the US for cryptographic matters was very high. So who knows? There's a hint that they might have used it. Who knows?
Maybe you could tell us a little bit more about what you're working on now, what problems you're solving, what's keeping you interested.
Yeah. So I work on various fields actually. Because I use mathematical analysis to tackle problems in number theory, I also publish works in pure mathematical analysis. Because what we do in analytic number theory, that's how it's called, is we use methods of mathematical analysis to tackle problems that are number theoretic flavor. So if you read the paper of number theorists, it's like mathematical analysis. So I try to tackle also problems in pure mathematical analysis. Now, my work in number theory is related to various problems that I work on simultaneously. One is the Riemann's hypothesis. It's something that is relevant also to what I did in my PhD. It's something called the Nyman-Burling criterion for Riemann's hypothesis. It's an equivalent statement. If the Nyman-Burling criterion is true, then Riemann's hypothesis is true. So part of my work is in that direction. Another part is related to Goldbach's conjecture. So Goldbach conjecture is one of the most famous problems in number theory. Of course, it attracts the enthusiasm of amateurs, also mathematicians, mathematical enthusiasts, because the statement is deceivingly simple. And after the book with Nash was published, I received dozens and dozens of letters of people who thought that they solved Riemann's hypothesis of the Goldbach conjecture. Because the statement of Goldbach conjecture, there are two conjectures actually, is very simple. Every even integer can be expressed greater than a specific number. Every even integer can be expressed as the sum of two primes, a binary Goldbach conjecture, and every odd integer can be expressed as the sum of three primes, the ternary Goldbach conjecture. This part was semi-proven in the 1930s. Namely, we knew that it was true for sufficiently large numbers. It was completely proved, meaning for all numbers, in 2013. The binary one is wide open. So anyway, I worked on the ternary. It has been proven, but we say every odd is the sum of three primes. What type of primes? So we want to see what's going on there. What type of primes can actually enter in this triplet? So some of the work is on Goldbach conjecture. Some other work is on gaps of primes. Without going into more details, things that are related to the distribution of primes, so that we get a greater understanding of how primes are distributed among the rest of the integers, which has been a problem very important for thousands of years. I mean, the ancient Greeks came up with the concept of a prime. The primes are infinite in number. The fundamental theorem of arithmetic. So we know these things from the period of Euclid. But still, until today, primes their behavior is extremely mysterious to us.
Yeah. And could you tell us a little bit about practical applications of prime numbers? Why are they important?
Sure. Okay. So in cryptography, generally, we are based upon our knowledge of what we don't know. Right. So what we believe that we don't know, publicly or not, and that we believe that our ignorance on it will remain deep for sufficiently long time to base a crypto system on this. An example, a cryptographic example of number theory application, is factoring. The fundamental theorem of arithmetic states that every natural number can be expressed in a unique way, that's a key, as a product of powers of primes. Product of powers of primes. So for each number, there are specific primes that compose it. Mm-hmm. So prime numbers are the building blocks of all integers. Okay, good. So if I give you the number, can you find the prime factors?
Me or hypothetically?
So generally, the answer to this is it's extremely hard to do so.
That was my answer too.
Specifically for the so-called semi-primes, namely something that seems simple, but it's one of the most difficult cases. N is equal to the product of only two primes of quite similar size, p times q. So if I take p huge, q huge, multiply them, something happens like this. I have the result n. I keep p and q secret. Can you find p and q? That's extremely difficult to do. And that's, for example, one of the basic ideas behind a crypto system like RSA, which is very widely used. And now the knowledge about the distribution of primes, all this research is relevant to this. So if we get very good understanding, deep understanding on how primes are distributed, we'll get deep understanding about functions like the Euler-Toschen function. And if we were able to approximate the Euler-Toschen function very well, we would break RSA. So, and there are other also cryptographic applications of number theory, but of other fields as well. So in cryptography, that's, of course, I sacrifice a bit rigor here, but in order to make it understandable, there's a problem that we think that's extremely hard to resolve. So we go one direction, not the other. And we use that idea to build an algorithm around it.
Okay. And now you said RSA is very widely used.
Yeah.
What are some of the common applications? Where would we see it?
For credit cards, email. Yeah. So wide applications. Yeah.
Every day. Okay. And now you're saying there's one method to break it would be to solve this problem. What about, I mean, you hear a lot on the news these days, brute force, cryptography breaking, the interaction with this and maybe...
Yeah, brute force in that specific case wouldn't work. As I mentioned in my talk, it would take a multitude of the age of the universe with brute force, but it depends what brute force, what do we mean by brute force? If we actually use very clever ideas and mathematical theorems that we come up so that we work our way around obstacles, then we'll, of course, reduce the time. That's what we try to do, to find ways so that we can construct what we called a polynomial time algorithm to tackle this. Polynomial time means fast, in a sense. But this doesn't exist yet, because our understanding of the distribution of primes is not deep enough. Brute force is not sufficient, because the computer is not intelligent. I mean, it does what we tell it to do. It has our theorems in it.
Mm-hmm.
So I don't need the
novel approaches is sort of off limits.
Excuse me?
Create novel approaches is a little bit off limits to the artificial side of things at this stage.
Yeah, at this stage, except publicly at least.
Mm-hmm.
Who knows? Well, if someone can factor efficiently somewhere in the world and they didn't tell anyone,
could be.
You never know.
Another Nash example.
Yeah.
Yeah.
Who knows?
Very cool.
Yeah.
Hey, I'm curious. So, of course, we talked earlier about the impact of your father on your life in mathematics. Do you think of a few other pieces along the way that really piqued your interest in this field? And how would you communicate your enthusiasm or your love of mathematics to the next generation?
Okay, interesting question. First of all, I just always did in math what I liked. That was a very important aspect. As I mentioned earlier, the first class I was involved in number theory was the one I was teaching. This might say a lot, because when you get introduced to various things from someone else, then you get his take on it. That might be awesome if he's a great professor, or not. Who knows? I mean, I always had the opportunity, I was lucky enough to choose, and also the professors I had helped a lot, both for my PhD, also when I was in the team of professors afterwards, after my PhD and so on, before I became professor myself, that they gave me freedom. That makes a world of difference. And if in mathematics, in pure math, if you don't do what you like, don't do it. I mean, what's the point? All right. But if I have to give a piece of advice, not about mathematics, not about science, but generally, there is a misconception, let's say, to people and parents, also in Greece, I hail from, that people think, I should do this or that, become a lawyer or a doctor of medicine, or, do what you like. This is going to seem like a cliche, but I cannot stress the point enough. You have to find the thing that you love, and then become the best at it, or as good as you can. Because if you find what you love and then you excel at it, then you'll do well. Then, because you will obtain value there, and then this value will be translated in a good life and so on. Do what you love, and then excel at it. Don't because people take the advice of this guy and the other guy to become lawyers or bankers, or do what you like, and then if you really like it, you might be playing the flute. You will be the best, right? That's my advice.
Very good. And now this sort of touches on another topic you mentioned, which is sort of, well, you lived it, interdisciplinary transfer, and also some of your heroes as well, also physics interests or physics backgrounds. What can you tell me about, is there a fresh perspective that the interdisciplinary exchange offers to the field of mathematics, or what's your take there?
It's not a one-way direction, in a sense that we often don't look for the interdisciplinary aspect, we stumble upon it. And it's amazing when it happens. It's like a miracle. So even for the thing I mentioned earlier, the Montgomery percorrelation conjecture, which is statistical percorrelation between zeros of the Riemann zeta function. So it's at the heart of one of the most important problems in mathematics, Riemann's hypothesis. When Montgomery had that discussion with Dyson in 1972, they saw that, oh my God, that percorrelation that Montgomery was observing was not just similar, but identical to the percorrelation between eigenvalues of random Hermitian matrices that Dyson had found 10 years earlier while studying physics.
Mm-hmm.
So showing a completely unexpected connection between math, physics, probability theory, and statistics. So you stumble upon those things. Of course, you have to be looking, in a sense. Montgomery discussed with Dyson. So a mathematician discussed with a physicist. So if mathematicians mingle together, biologists, astronomers, physicists, or whatever they might be, they might not stumble upon anything, but still they will have a very pleasant discussion. Or something miraculous can come out. Because a mathematician cannot be simultaneously a biologist, a physicist, an astrophysicist, a musician, right? So the good thing is that this encourages collaboration and communication between people working in completely different fields. And at the Institute for Advanced Study, they had this program. They had a program called Program in Interdisciplinary Studies. I was part of that program. So the atmosphere there was amazing because mathematicians could talk with all these different people. A physicist with a mathematician, a psychiatrist with a musician, a biologist with a mathematician. And you take their take on, you would view their take on various things. Yeah, amazing. Yeah.
Hey, Michael, thank you so much for being here. It's been a real pleasure. I've learned a lot, and I look forward to connecting again in the future.
Yeah, that was great. Thanks for having me.
My pleasure.